All right, so here's where we left off. We found that the reason that we can use the Henderson-Hasselbalch equation here is because I have concentration, a little bit of the acid, a little bit of the conjugate base, and so that allows me to do that. All right, so what I'm going to do is I am going to just start plugging in. So I know what my pH is. We said at the very beginning it was 4.37 is equal to the negative log of the Ka, which is 1.8 times 10 to the minus 4 plus the log of the conjugate base or the salt divided by the acid. Now, what's great about this now is this is what I'm after right here, because if I find the molarity of my acid, then I can get my moles. I just calculated that. So let's go on. Let's go here. Let's plug everything in. So I get 4.37 is equal to the negative log of 4.37 is equal to 3.74 plus the log of HCOO minus divided by HCOOH. I pull this over here and I get 0.625 is equal to the log of HCOO minus divided by HCOOH. Now, once I'm here, I've got to undo this log. So remember, like we did with ease, we're going to raise both sides. We're going to have them be the exponent to the 10th power. When I do this, if I plug this in my calculator, let's do that. So I just want to show you. Second log of 0.625 equals 4.22. So 4.22 is equal to, when I take the base of 10 and raise it to the log, I'm basically undoing all of that, and I get is equal to the concentration of my anion divided by my acid. Now, I don't necessarily have my concentration. What do we calculate over here? When we did this problem, we calculated the number of moles of this, which is here, and I need to look at what the volume of my solution is, right? I've got 15 milliliters and 25 milliliters, so 25 plus 15 is 40, so I've got 40 milliliters altogether. So basically what I've got to do to get molarity, because remember brackets are molarity, I have this is going to be 2.25 times 10 to the minus 3 moles divided by 0.040 liters divided by the concentration of COOH. This is all algebra. When I work all that out, I get the concentration of COOH is equal to 0.0133 molar. But that's still not moles. The question is asking for the number of moles. So I take 0.0133 moles per liter, and I have 0.040 liters. That should give me moles, which is 5.33 times 10 to the minus 4 moles. That's the hardest one. So let's look at a summary. Now what I've done here is I've added some arrows. Remember that we are at this point because we were able to take advantage of the fact that we had a ratio of these two species. Okay, one more quick thing I want to go over. that I got a lot of questions in tutorials about that people didn't understand. I want to look at, let's see, this. Now, when you use a buffer, why is it that a buffer works? What is the conceptual reason for this? So what I'm going to do is I'm going to write this in a different way. I'm going to take my buffer, I'm going to put it in a beaker, and then I'm going to add my solutions, and maybe this will help. So what I did is for the students is I drew a picture. All right, so I've got this flask, and what I did is I made a buffer, and I've got a little bit of HF in here, and I've got some F minuses in here. That's my buffered solution. Now, what I'm going to do is I'm going to add some acid. Now, under normal circumstances, I'm bad at drawing these, if I were to add H, it would go into solution, that would be my acid, and the pH would be very low because that's dissociated. But that's not what's going to happen here. These are sitting there waiting, and this can either react with HF or F minus. Well, this is the acid, it's going to react with the base. So what's going to happen is that H plus is going to react with F minus, and it's going to be equal to HF. So what do I have now? Instead of having that, which is low pH, I snatched it up and make this, which is higher pH. It snatched it up and buffered it and kept it from making just the dissociated acid. I can do the same thing with OH. When I add OH minus, it's going to react with this one. So HF plus OH minus is going to give F minus plus H2O. If I had added this to a regular flask like this, I would have had OH minus in water, and this would have been a high pH. But instead of that, I'm making this, and this has a lower pH. So either way, I'm buffering because instead of these species in solution, I have these species in solution, and that keeps my pH close to the pKa of this conjugate system.